Well, good morning. Wednesday, May 27th, 2020. It's hump day. Haven't had that one in a while. All right. Learning targets. So, given composition information, I can calculate empirical and molecular formulas. So, why don't you go ahead, pause the video for a second, write down these basic steps. I'll read them through you just in case, you're having trouble seeing them. But this is determining empirical formula, which is another name for the simplest formula. We're going to change percent information to masses, convert mass information to moles. We will simplify the mole ratio by dividing each number of moles by the smallest. We'll see what that means by example. If necessary, we'll multiply each number of moles by a small whole number, and then we're going to write our empirical formula. Again, pause, write these down. Hopefully you've done that. So, here we go. We're just going to work through it by a sample. A compound is found to contain 36.48% sodium, 24.41% sulfur, and 38.02% oxygen. Find its empirical formula. So yesterday you were calculating the percent composition of problems. This is basically the reverse. Now you got percent composition. Can we get back to the formula? And we can. Okay. So I'm going to write down this information in our workspace, and I don't know what I'm thinking. I don't have to write it down because I can just go, ta-da, there it is. So there's the starting information. And if you look at step one, it said to change percents to mass. All right. Percents apply no matter how much you have. Okay? If I have a little grain of salt, it's got a certain percent of sodium and a certain percent of chlorine. If I have a huge pile of salt, it's still the same percent of sodium, the same percent of chlorine. Doesn't matter how much you have. Okay, we figured out water the other day was just over 11% hydrogen. So here's some sample of water. Of whatever this amount is, it's just over 11% hydrogen. That little bit I just dribbled in my hand is just over 11% hydrogen. It doesn't matter how much you have. So the reason that's important is if it doesn't matter how much we have, as long as we're starting with percents, let's choose a number that makes our math easy. What if I imagine having 100 grams of whatever compound this is? Of that 100 grams, 36.48% of it is sodium, which means it's going to be 36.48 grams of sodium and 25.41 grams. So when I say change percent to grams, literally, I'm saying change percents to grams. If you have percent information, just cross that out and replace it with grams. Second step says grams to moles. All right, so remember our islands? We had mole island, and we had mass island, grams, okay? And there was a bridge to get from grams to moles, which said divide by the molar mass, okay? And the molar mass is that same as the formula mass that you get from your periodic table, or for a compound when you add up from the periodic table. So here's what we do. If I want to change that many grams of sodium to moles of sodium, I had to look up sodium on the periodic table. It's 22.99 grams per mole. Sulfur is 32.07 grams per mole, and oxygen is 16.00 grams per mole. Okay, I had to look up each of those. It's 3 different mole conversions, but a mole conversion is just a real basic conversion. And I can multiply these out, and here's the numbers I get. Now, here's a mole ratio. And I want you to understand, when you write down a formula, that's fundamentally what you have is a mole ratio. If I were looking at water, and it's H2O, that means there's 2 atoms of hydrogen for 1 atom of oxygen. If I had a bigger sample of water, if I had 200 atoms of hydrogen, there'd be 100 atoms of oxygen. If I had 2 billion atoms of hydrogen, there'd be 1 billion atoms of oxygen. Or if I had 2 moles of hydrogen, I'd have 1 mole of oxygen. The formula gives us a mole ratio. Well, I have a mole ratio here. Can I write my formula? Have you ever seen a formula like this? Na 1.587, S 0.79230, 2.376. That's a formula, but it's ugly. Okay? We want a whole number formula. We want a simple whole number formula. And so we got to think of basically how do we simplify this ratio. And the trick is take whatever is the smallest number here. That's this one. And divide. Now, if I divide everything in a ratio by the same thing, the ratio stays the same, right? Now, look mathematically, this one becomes a 1. And this one becomes a 2, and this one becomes a 3. Now, if you punch it into a calculator, it might say 1.99. You have to recognize that, oh yeah, that looks for all practical purposes like a whole number. Okay? Now, there are going to be times where it doesn't come out to a whole number here. Watch out for simple fractions. I mean, like a 0.5, a 0.33, a 0.67. Simple fractions, but it shouldn't just be anything. It should be close to either a whole number or a simple recognizable fraction. We'll get to, if it's a fraction, we'll come back with another problem. 2 to 1 to 3, hey, that's a much better mole ratio to work with. Na2S1O3. Oh, and I can put a name to that. Gee, I know that's a sulfite ion, sodium sulfite. Boy, if I can put a name to it, I'm feeling pretty good about what I just did. This is the steps. We changed the percents to grams, we changed grams to moles, we simplified the mole ratio, and we wrote a formula. Okay? Let's just look through this one. This was, I think, number 3 on the worksheet that you're going to get. It says analysis indicates that it contains 1.04 grams of potassium, 0.70 grams of chromium, and 0.82 grams of oxygen. So notice, it gave us grams. So step 1 that says change percents to grams, we're already in grams. We don't have to do step 1 at all. Don't let that confuse you. I've seen students who go and add this all up and then try to figure out what percent potassium is so that then they could redo this problem. And that's not at all necessary. That's just making a whole lot of extra work for yourself. If you're given grams, take it. Now, convert the grams to moles. So the stuff in black would have been the original ones. The smallest one was the 0.013. So I divided each of those. So that's about 1. And this guy's about 2. And this guy's about 4. And again, they were really, really, really close. I don't round these off much. But if that's the case, then I know I got K2CrO4. Gee, that'd be potassium chromate. All right, let's try this one. 52.92% aluminum, 47.08% oxygen. Looking for the empirical formula. So I write down my original. I was given percents, so I'm going to change that to grams. Okay. I got grams, now I'm going to change to moles. So I look up on the periodic table to find aluminum and oxygen. I do my math. What happened? There we go. I had an extra page in there somehow. All right. So now here's my mole ratio. I want to simplify it. This is the smaller number, so let's divide them both. And so that, the smallest always comes out to a 1. But this one didn't come out to a whole number. It came out to 1.5. So it's sort of like I have a ratio now where I say it's ALO 1.5. And that's still not acceptable for a formula. How can I have a ratio 1 to 1.5? I want to turn that into a whole number ratio. If I've got a 0.5, Let's double it. Let's double, but remember, when we have a ratio, you got to do the same thing to all parts. So I'm going to double that to a 2, and I'm going to double that to a 3. Oh, yeah, you know, Al2O3, that would be like one of these for every 1.5 of these. And when you look at the formula, oh yeah, aluminum forms +3 ions, oxide forms -2 ions. This all works. Okay? All right. I am going to keep going to the next step where we're finding molecular formula. And you notice for molecular formula, the first 5 steps are the same. So you have to find an empirical formula first. But I added 3 steps. So let's go through them. Add up the mass of the empirical formula. So you just figured out an empirical formula, add up its mass. We're going to need one more piece of information to find a molecular formula, and that is a molecular mass. So you'd have to be given that. But then, take that molecular mass and divide it by that empirical mass you just found. And that's going to tell you how many times bigger the molecular formula has to be. And so then we just increase the empirical formula proportionately. I'm going to just say, here's a compound. It's called benzene. It's got alternating single and double bonds in a carbon ring, a 6-atom ring, and then 1 hydrogen on each. And so if you count up, the molecular formula is C6H6. The empirical formula only gives us the lowest ratio, the simplest ratio. So if we were doing an empirical formula calculation for this, we'd come up with CH. But if it's a molecular substance, the molecule may be actually involving more atoms bonded together than that. See, while this is the lowest ratio, and for ionic compounds, the lowest ratio is all we need. But for molecular compounds, covalent compounds, there could be more atoms bonded together. So if I figured out that the empirical formula was CH, and this would have a mass of about 13 units, okay? Then what happens is I'd have to give you the molecular mass. And the molecular mass of benzene is about 78 units. And you say, well, 78, how many times does 13 go into there? And you start guessing and you say, well, what about 6? Well, 6 times 3 is 18, 6, 7, 0. Oh, 6 goes in there exactly. So our molecular formula is 6 times bigger than our empirical formula. So we increase proportionately both the carbon and the hydrogen, C6H6. So let's look at a problem. So we got the formula mass of compounds, 92.0. So that's that extra piece of information. Analysis says that you have 0.606 grams of nitrogen and 1.390 grams of oxygen. And we're going to find its formulas. So I'm going to start out, I wrote down its information. We were given grams, so don't worry about those percents ever. We're going to change grams to moles. Look them up, periodic table. Divide out, here's my mole ratio. Okay, simplify it. Here's my smaller number. Divide both by that, and we got a ratio of about 1 to 2, which means my empirical formula is NO2. Okay, now we're going to look at the molecular formula. So let's add up this mass. And for this, we can usually be a little bit approximate. So nitrogen I know is about 14, and each oxygen is 16. 16 times 2 is 32, 46. Yeah, that's got a mass of 46 units. And we were told that the compound actually has a mass of 92 units. And you might be able to just do some mental math and say, well, how many times does 46 go into 92? If you can't do the mental math, then take a calculator. What it ends up being a 2. So our molecule is twice as big as this. So our molecule is N2O4. That's empirical and molecular formulas. I've got some examples here that you can be looking through. You can watch this multiple times. You're going to practice a couple, turn something in for a grade. I'll get that in your assignment. Take care.